What if I told you that this year, mathematicians figured out how to pack oranges more efficiently?
More efficiently.
Yeah, but like in dimensions we can't even see.
Okay, that sounds a little wild.
It does, right. But that's actually what we're going to be diving into today, the wildest math breakthroughs of 2024.
Sounds fun.
We've got spheres getting cozy in unimaginable spaces. We've got hidden patterns emerging from seemingly random numbers and a mathematical Rosetta Stone that's been decades in the making.
It's a pretty remarkable year for mathematical discoveries, for sure.
So let's start with those oranges,
Okay.
or spheres to be more precise.
Right.
Imagine you're trying to fit as many tennis balls as possible into a box.
Okay. Yeah.
You probably arrange them in a pyramid shape.
Mm.
That's the most efficient packing in 3 dimensions.
Right.
But what happens when you go beyond our familiar 3D world?
That's where things get really interesting and mind-bogglingly complex.
Yeah.
For decades, mathematicians have been trying to crack the code of sphere packing in higher dimensions. It's not just a theoretical puzzle, though.
Right.
It has real-world implications.
Okay, so why should I care about how spheres pack in, say, 8 dimensions?
Good question.
Does this affect my daily life?
More than you might think.
Really?
Yeah, so dense sphere packings are essentially the same as efficient error-correcting codes.
Okay.
And these are vital for everything from reliable data storage to clear communication signals.
So it affects my phone?
Yeah, so it actually could make your phone calls drop less often.
Okay, I'm listening.
But even more importantly,
Yeah?
it challenges how we think about problem solving in general.
All right, I'm intrigued.
Okay.
So what's the big breakthrough in sphere packing this year?
Well, for a long time, the focus was on finding perfectly ordered arrangements,
Okay.
especially lattices.
Lattices.
Yeah, these are highly symmetrical patterns, kind of like a perfectly aligned grid.
Gotcha.
And in some specific dimensions, lattices are the best way to pack.
Hmm.
Marina Vyazovska actually proved that for 8 and 24 dimensions back in 2016.
Okay, but what about all the other ones?
Right, so for most dimensions, it remained a mystery.
So what changed in 2024?
Well, that's a great question.
Did someone finally figure out the perfect lattice for all those other dimensions?
Not exactly.
Uh,
This is where it gets really wild.
All right, lay it on me.
Instead of forcing order, mathematicians embraced chaos.
What?
Yeah,
They started placing sphere centers randomly.
they did.
Wait, randomly.
Yeah.
Like just throwing darts at a board and hoping for the best.
Kinda.
That doesn't sound very mathematical.
I know it does seem counterintuitive,
Yeah.
but there's a brilliant logic behind it.
Okay.
You see, in high dimensions, things get so complex
Yeah.
that even the tiniest imperfection in a lattice can throw off the entire packing.
Huh.
Randomness introduces a level of flexibility that allows for much denser arrangements.
But how do you even make sure that randomly placed spheres don't overlap? That sounds like a recipe for a jumbled mess.
It does, but that's where the ingenuity comes in. They used a tool from graph theory
Okay.
called the Rödel nibble.
Rödel nibble.
Yeah, imagine you're trying to color dots on a page,
Right.
making sure no two dots that are too close together have the same color.
Gotcha.
The Rödel nibble helps you do that strategically, ensuring a good spread.
Okay, so they're using this graph theory tool to prevent the spheres from overlapping.
Exactly.
But how does that actually lead to a denser packing?
Okay, so think of each sphere center as a dot on your graph.
Okay.
If two dots are too close,
Yeah.
they're connected by a line, meaning the spheres would overlap.
Okay.
The goal is to find a large group of dots with no connecting lines.
Right.
That represents a successful non-overlapping arrangement of spheres.
So by analyzing these random graphs, they found surprisingly dense packings.
Yeah.
Better than anything achieved with those perfect lattices.
Exactly. It turns out that in many high dimensions, embracing a bit of messiness can lead to more efficient solutions than striving for perfect order.
Huh. So messy solutions winning out in high dimensions.
It's a real paradigm shift.
It is mind-blowing.
Yeah.
So messy solutions winning out in high dimensions. What does that mean for the rest of us? Is this just a theoretical curiosity?
No, it's not just a theoretical curiosity.
Or are there real-world applications?
Oh, there are definitely real-world applications.
Like what?
Remember those error-correcting codes we talked about?
Yeah.
This breakthrough could revolutionize how we design them, leading to more reliable data storage and transmission.
So my Netflix streaming without buffering.
Exactly.
Get behind that.
Are there any other areas where this could have an impact?
I don't know, are there?
Yeah, so it also changes how we approach other high-dimensional problems.
Okay.
Imagine trying to design a robot arm with multiple joints
Okay.
or analyze complex data sets with hundreds of variables.
Right.
These are essentially high-dimensional problems, and this new understanding of sphere packing could lead to more efficient solutions in those fields as well.
Okay, so we've got messy solutions reigning supreme in higher dimensions with potential impact on everything from data storage to robotics.
Uh-huh.
That's a pretty wild start to our deep dive.
And we're just getting started.
Oh, really?
Now let's shift gears from the world of spheres to the fascinating realm of number sequences.
Okay.
Imagine you have a giant set of numbers, seemingly random,
Okay.
but what if I told you that if that set is large enough, it has to contain certain patterns no matter how chaotic it appears?
Now that sounds like a magic trick.
It does, doesn't it?
But hold on, let's unpack this idea a bit further.
Okay.
Okay, so you're saying that even in a seemingly random jumble of numbers, there's a hidden order waiting to be discovered.
Yeah, it is.
That's a pretty mind-bending concept.
It is. It's like
Yep.
it's like finding constellations in the stars.
Okay.
At first glance, it's just a random scattering of points.
Right.
With the right perspective,
Well,
you can see patterns and connect the dots to reveal something meaningful.
I like that analogy.
Yeah.
So what kind of patterns are we talking about here?
Specifically, we're talking about arithmetic progressions.
Okay.
These are sequences where each number is bigger than the last by the same amount.
Okay.
Think 3, 7, 11, 15.
Okay.
Each number is 4 greater than the one before it.
Right. I remember those from math class.
Yeah.
But how do we know these progressions have to exist in any large set of numbers? It still seems kind of random to me.
That's where a famous theorem called Summeradi's theorem comes in.
Okay.
It was proven back in 1975,
Uh-huh.
and it states that any sufficiently large set of integers must contain arithmetic progressions of a certain length.
Okay.
It's not just a hunch, it's a mathematical certainty.
So if I have a giant list of numbers, like say all the winning lottery numbers in history,
Right.
I'm bound to find some arithmetic progressions hiding in there somewhere.
Exactly. Of course, finding them might be a bit of a challenge,
Right.
but they're guaranteed to be there.
Ah.
The question that has puzzled mathematicians for decades is, how big does a set have to be before these progressions become inevitable?
Right, because Summeradi's theorem just proved that they exist.
Yeah, it proved they exist, but it didn't tell us the exact threshold.
And that's where the 2024 breakthrough comes in.
You got it.
Okay.
This year, 3 graduate students made significant progress in tightening the bounds on that threshold. They found a new way to calculate just how large a set needs to be before you're guaranteed to find arithmetic progressions of a specific length.
Wow. 3 grad students cracking a problem that had stumped seasoned mathematicians for decades.
I know, it's pretty impressive.
That's impressive. What was their secret weapon?
They used a clever combination of combinatorial and analytical techniques, breaking down complex sets into more manageable chunks.
Okay.
To reveal those hidden progressions, it's like taking a giant jigsaw puzzle and finding a new way to sort the pieces,
Okay.
making it easier to assemble the final picture.
Okay, so we've gone from pecking spheres in high dimensions to uncovering hidden patterns in number sequences. Both pretty abstract concepts, to be honest.
They are.
But what does this breakthrough with arithmetic progressions actually tell us about the world?
Well, it goes beyond just number sequences.
Okay.
It speaks to a fundamental principle about order and randomness. Even in systems that appear chaotic, there's often a deep-seated structure waiting to be uncovered. The more we learn about how these patterns emerge, the more we understand the underlying rules governing our universe.
That's a pretty profound thought.
Yeah.
So are you saying that by studying these abstract mathematical concepts,
Right.
we can gain insights into the very fabric of reality?
Absolutely. And it gets even more fascinating when we start connecting different areas of mathematics together.
Oh, okay.
Which brings us to our final breakthrough.
Right.
A discovery that's been hailed as a mathematical Rosetta Stone.
Okay.
It's called the geometric Langlands conjecture.
Okay, now that sounds intimidating.
It is mouthful.
Geometric Langlands conjecture.
Yeah.
We're definitely venturing into the realm of serious math now.
Yeah, a little bit.
Break it down for me. What is this conjecture all about?
So imagine if you could find a universal translator for mathematics.
Right.
A way to connect different branches of the field that seem completely separate at first glance.
All right.
That's essentially what the geometric Langlands conjecture aims to do.
Gotcha.
It's about finding a deep underlying unity between seemingly disparate areas like number theory, geometry, and representation theory.
So instead of just studying numbers, shapes, or abstract algebraic structures in isolation,
Yeah.
this conjecture tries to find a way to translate between them, to see how they relate to each other on a deeper level.
Precisely. It's like finding a hidden code that reveals the interconnectedness of all these different mathematical languages.
Okay.
And for over 30 years, this conjecture has been a major puzzle, a challenge that has driven mathematicians to push the boundaries of their understanding.
And I'm guessing this year, someone finally cracked the code.
They did. A team of 9 mathematicians, after years of effort and collaboration, produced a monumental proof of the geometric Langlands conjecture.
Okay.
And let me tell you, this is no ordinary proof.
Really?
We're talking about an 800-page behemoth.
800 pages.
800 pages.
That sounds more like a Tolstoy novel than a math paper.
It does, doesn't it?
What kind of mathematical wizardry did they have to conjure up to solve this thing?
It's less about magic and more about a profound depth of understanding
Okay.
and a willingness to collaborate on a massive scale.
Okay.
The proof involves some incredibly abstract concepts like sheaves, categories, and representations.
Okay.
But at its core, it's about finding a way to classify these objects, to organize them in a way that reveals the hidden connections between different mathematical structures.
So they're basically creating a map of the mathematical universe, showing how all these different continents of knowledge are linked together.
Exactly. That's a great way to put it.
That's a pretty awe-inspiring achievement.
It is, and the implications go far beyond just proving a conjecture. Okay. It opens up entirely new avenues of research, new ways of thinking about mathematical problems, and potentially new connections to fields we haven't even considered yet.
Okay, so I'm definitely starting to see a theme here.
What's that?
Messy solutions, outperforming perfect ones,
Yeah.
hidden patterns emerging from chaos,
Right.
and now a mathematical Rosetta Stone that unites different branches of math.
It all ties together.
2024 has been a wild ride for mathematical discovery.
It really has, and what's most remarkable is that these breakthroughs, as diverse as they are, all point to the power of human ingenuity to tackle immensely complex problems. Whether it's through randomness, intricate arguments, or grand unifying theories, mathematicians are constantly pushing the boundaries of what we know and how we think.
That's pretty inspiring.
Yeah.
But I have to admit, I'm still struggling to grasp the real-world significance of a theory as abstract as the geometric Langlands conjecture.
Okay.
Does this actually affect my life in any tangible way?
Well, it's not always about immediate practical applications.
Yeah.
Sometimes it's about expanding the frontiers of human knowledge, about exploring the universe of ideas and pushing the limits of what we thought was possible. Think of it like the first moon landing.
Okay.
It didn't immediately solve world hunger or cure diseases,
Right.
but it fundamentally shifted our perspective and opened up a whole new realm of possibilities.
That's a great point.
Yeah.
So are you saying that sometimes the most profound discoveries are those that challenge our assumptions and inspire us to think differently, even if we can't immediately see their practical use?
Exactly, and who knows what groundbreaking applications might emerge from these theoretical advances in the years to come.
Yeah.
The history of science is full of examples where seemingly abstract ideas eventually led to transformative technologies and solutions to real-world problems.
All right, you've convinced me.
Could be.
I'm officially on board with the idea of embracing the power of abstract thought.
All right.
But before we get too carried away with the philosophical implications,
Okay.
let's bring things back down to earth and recap what we've learned today.
Sounds good.
We started with spheres getting cozy in unimaginable dimensions. Yeah, we started with spheres getting cozy in those unimaginable dimensions you were talking about.
It really stretches the imagination.
It kind of blew my mind a little bit, but we saw how embracing a bit of randomness, you know what I mean, actually led to more efficient solutions than those perfectly ordered lattices.
Yeah, those perfect lattices we thought were the answer.
And then we moved on to uncovering those hidden patterns in seemingly random numbers.
Right.
With those arithmetic progressions.
Yeah, those are fun.
It was a lot of fun, and that highlighted a fundamental principle about order emerging from chaos, a concept that reaches far beyond just number theory.
Yeah, exactly. It kind of shows up everywhere when you start looking for it.
And finally, we tackled the granddaddy of them all, the geometric Langlands conjecture, a mathematical Rosetta Stone that connects different branches of math in ways we're only beginning to understand.
Yeah, it's really a game changer.
It truly is. It's a monumental achievement
Right.
that really showcases the power of human collaboration and ingenuity.
Yeah, all those mathematicians working together
For years.
to finally crack this thing. It's amazing.
I'm still trying to wrap my head around the idea of a mathematical theory being 800 pages long.
It's a lot of pages.
But hey, it's a testament to the complexity and the depth of this discovery, right?
Absolutely. It's a monumental piece of work.
It is.
Yeah.
But beyond the sheer intellectual achievement, it's the implications of these breakthroughs that truly excite me.
Yeah, where do we go from here?
Exactly. So what kind of doors do these discoveries open up? What's next on the horizon for the world of math?
Well, think back to those super dense fear packings achieved through randomness, right?
Yeah.
Can we push those densities even further?
I don't know, can we?
That's a good question.
I like it.
Are there other areas where embracing chaos might lead to unexpected solutions?
Hmm. More chaos, I'm game.
Exactly right. It's all about challenging our assumptions.
What about those arithmetic progressions? Now that we have these tighter bounds on them,
Right.
is it possible to find the exact threshold where those patterns become inevitable?
That's the holy grail right there.
Yeah,
I think that's a question that will likely keep mathematicians busy for years to come.
for sure.
And with the geometric Langlands conjecture now proven,
Yeah.
what new connections can we forge? What other mathematical mysteries can we unlock using this Rosetta Stone?
It feels like we're just scratching the surface of what's possible.
Absolutely. And that's what makes mathematics so endlessly fascinating.